Good morning and welcome to the Let's Talk Lignin webinar. My name is Chris Walton. I'm the CEO of the Center for Research and Innovation in the Bioeconomy. CRIBE is an independent nonprofit with a mandate to support innovative uses of Ontario's forest biomass. Since 2009, CRIBE has been actively supporting applied research in the extraction and utilization of lignin from woody biomass. And as a result, we're seeing significant interest and uptake from the value chain in the use of this innovative new product. And the current, our panelists today are world leaders in R&D in the subject matter. And I hope you enjoy the webinar, and we look forward to continued collaboration and engagement on the subject matter. So I'd like to pass this over to Mike Barton, who is the Next4 coordinator, to talk a little bit about the format of the webinar and introduce the speakers. Thank you.
Thanks, Chris. Hi, everyone. Thanks for tuning in today. My name is Mike Barton. I'm the Next4 coordinator here at CRIBE. So Next4 is an industry collaboration network that's been designed to accelerate new technologies in Ontario's bioeconomy. We're proud to continue on the success of the conversations we started with our high-performance lignin forums way back in 2018 with this webinar today. So an objective of Next4 is to be an open information sharing and collaborative environment for stakeholders in the industry, government, researchers, and others. As a reminder, Next4 users will have full access to this webinar recording, as well as this live presentation on our online portal, along with a wealth of other informational materials. Be sure to sign up if you haven't done so already. It's free to register as a user. So just some housekeeping for today's webinar. Today's presentations have been pre-recorded, so there will be a live Q&A period at 11 a.m., approximately 11 a.m., that the guest speakers have made themselves available for. To post a question to the panelists, you can participate by posting a comment in the comment section of the LinkedIn or YouTube live stream videos when we enter the Q&A period. Please hold your questions until we enter the Q&A period so we can collate them, and we'll do our best to answer all of them. However, we only have 30 minutes today for questions. With that, I'd like to get started, and I'll introduce our first guest speakers from FP Innovations. So Natasha Mongeau is a business development manager at FP Innovations. Her role is to identify and create innovative partnerships and win-win business scenarios for the Canadian forest sector growth in emerging and sustainable markets. She plans impactful strategies for bioproduct development in collaboration across other industries with a focus on lignin. Eric Olivier is also presenting for FP Innovations and is a scientific executive with more than 20 years of experience in directing research in the fields of chemistry, nanotechnology, process development, API manufacturing, drug design, and synthesis with bioproducts. Eric is an organic chemist and entrepreneur with a proven track record of accomplishments in program creation, management, and creative scientific approaches to new product developments. With that, I'll cue up the presentation here.
I'm Natasha Mongeau, a business development manager at FP Innovations, and I'm here today with Eric Olivier, the Senior Director of our Bioproducts Division. Our presentation will summarize FP Innovations' strategy for commercialization of forest-based lignin based on continued process improvements and development of applications. Our state-of-the-art facilities for processing, characterizing, and using lignin, both at laboratory and pilot scales, provide us with unique capabilities to advance the use of lignin in the everyday world. FP Innovations is a private, not-for-profit R&D organization that specializes in the creation of solutions that accelerate the growth of the Canadian forest sector to enhance their global competitiveness. We're deployed across Canada with our head office in Montreal. We have major labs in Quebec City and Vancouver, 8 pilot plants, and offices across Canada that are close to our members' operations. FP Innovations is serving over 90 members with an annual budget of $68 million. We have divided our operations in 4 innovation centers of excellence. The major projects we're actually driving in each of them are Internet of Forest for real-time connectivity in remote areas, automated harvesting machines through robotics, forest truck platooning to overcome labor shortage, mid and high-rise wood structure buildings with fiber-based materials for the envelope, For pulp and paper, we're developing new products for existing facilities such as stretchable papers, packaging, and tissue. Finally, we develop platforms for biosourced materials and chemicals, various applications and methods of production for those new biomaterials, which we can scale to commercial plants at our members' facilities. Working with members on the entire value chain directly at our members' facilities gives us a unique perspective and capacity to ensure that the improvement of the forest management respond to market requirements. We can help reduce costs at all levels to ensure competitivity of our Canadian industry. Our expertise spans the pulp and paper industry, forest operation, wood products, and since over 20 years now, the biosourced bioproduct sectors. Having two types of lignin offers an infinity of possibilities in terms of research and development, from animal feed to natural ingredients, wood adhesives, roads, and fine chemicals. Many research centers and universities are pursuing very promising projects, and we're seeing more and more of them getting to the market. We also know that for a non-forest industry to adopt a forest bio-based product, there's a need to ensure a steady supply of products that have the right characteristics. For the forest industry to invest in the production of bio-based products, there's a need for a demand in large quantity, the classic chicken and the egg challenge. Our business model to develop lignin-based applications is to work hand in hand with partners and end users to demonstrate new lignin-based product for a quick market adoption. Gosling, Beeling, Balashkin, and others have nicely portrayed the general opportunities for lignin applications according to potential volumes and prices. Looking at these and evaluating our capacity to fast track them to the market, we're concentrating our efforts only to a few ones. In developing our strategy, we looked at optimizing processes to produce lignin in large quantities at a competitive price and low carbon footprint. We're also looking into applications for high volume, even though they may sell at a lower price, and balancing it with higher value applications to increase the revenues of the Canadian lignin producers.
At FP Innovations, we're pursuing two distinct and very complementary approaches to forest-based biorefining. The first, a cellulose-based biorefinery approach, whereas lignin is a byproduct produced from the isolation of and evaluation of cellulose fibers in different applications. The second, a lignin-based biorefining approach, whereas cellulose derivatives, the sugars hydrolyzed from cellulose, are the byproducts, where the lignin that is produced is a near native, close to natural lignin with very distinct properties and distinct opportunities for applications. On the lignoforce system approach to creating value through craft lignin precipitation and purification, we benefit from two key steps. The first is an oxidation step, which reduces sulfur compounds and creates a much healthier work environment in the mill for producing precipitated lignin. The second is an acidification reaction, where we're able to coagulate, filter, and wash quite efficiently in a single step the lignin products and isolated in two distinct forms. We've implemented this not only on the pilot scale in Thunder Bay, Ontario, but as well in a commercial plant at West Fraser with a nominal production capability of 30 tons a day. This plant produces two distinct lignins, one which is a water-soluble hydrophilic alkaline form of lignin called lignin B, as well as a more hydrophobic and water-insoluble acidic form called lignin A. On the TMP bioprocess for lignin production, we're actually using a hydrolysis of cellulose that is done by enzymatic hydrolysis. The first step, we're starting with hardwood chips. Mechanical pretreatment is followed by a hydrolysis step through the use of enzymes. We're able to produce a very pure and non-toxic sugar, water-based sugar stream and a lignin product that is easily washed with water. The typical product coming out of the process today is a lignin carbohydrate complex, typically composed of 65% near native lignin. In Thunder Bay, we've also invested significant amounts in the pilot plant as well for the Lignin TNT bioprocess, isolation and purification pilot plant, where we're able to produce C5 and C6 sugar blends at the rate of 1 ton per week, as well as hydrolysis lignin, the same scale, 1 ton per week of lignin. Available products through both refinings on the craft side. The craft lignin, which is today brought to many applications as refined directly from the mill. It's composed of condensed small polymers that are adjustable for water solubility, are transformable in secondary transformations, and amenable to many, many applications. On the hydrolysis lignin, the product is of higher molecular weight, a near native lignin, close as natural as possible, wherein we have access to a non-condensed structure, easily amenable to break down into valuable monomers as well as functionalized oligomers. This gives us access to high purity fine chemicals, as well as refined applications, for instance, in animal feed and fisheries and so forth. On the research program, where our strategy is focused both on the process optimization and evaluation, as well as the applications. On the craft side, we're still addressing the recovery of CO2 from kilns in order to acidify the media and using the CO2 efficiently, reducing operation costs, evaluating lignin drying options as well. We are also working this year on the hardwood black liquors through the LignoForce process and evaluating these materials as well. On the application side, we're looking at new ways of including craft lignin and derivatives into adhesives and for different applications from wood panels and other polymer adhesion systems, as well as dispersants and concretes, the offset of bitumen and asphalt that we'll talk a bit more about in this presentation, and other applications like the use of lignins as coating materials, as well as carbon fibers. On the hydrolysis lignin platform, the hydrolysis biorefining approach is being evaluated for techno-economic considerations, the feasibility and scale. Pathways as well are being optimized for both hardwood and softwood, and looking at different mechanical approaches to cost reduction and processing. On the application side, for the as refined lignin carbohydrate complex applications straight from the mill, we're looking at animal feed applications. We're in the second phase trial for poultry and nursery pigs, as well as fish feeds. We're also in the second phase trials for adult salmon and shrimps. We're also considering the oligomers and some of the monomers for use in plastics and adhesives, as well as thermoplastic and other applications like accessing monomers for the fine chemicals and the polymer industries. As exemplified by this process that was achieved in Point Claire, hydrolysis lignin was brought to a depolymerized form and extract and purified to vanillin and significant yield with very high purity product. And this could be amenable to many different monomer transformation possibilities for the fine chemicals industry.
This lignin-based asphalt project is another example of how we're getting a product to the market. The concept of lignin as a partial substitution of bitumen in asphalt has been the object of many studies since the 1980s, with various types of lignin showing all kinds of advantages that could respond to the pavement industry's challenges. For example, in the Netherlands, they have tested and demonstrated lignin substitution ratios up to 50%. The objective of this project is to make a demonstration under our much colder northern climate, our Canadian regulations, and with the craft lignin that our industry can produce. We're not targeting 50% rate, as we already know that lignin responds very well at high temperature, but not as well at low temperature. Our assumption was a 20% substitution, but our initial lab results show that we should now target a 5 to 8% of craft lignin as is to ensure performance gains only. The project is being conducted with participants along the entire value chain to get an early buy-in by the industry, from lignin producers to road constructors and clients. By involving local producers, municipalities, and departments of transportation, we'll be able to obtain all information required by the industry to quickly adopt the new product. The producers will have had a chance to manipulate it and verify its workability under real commercial conditions. From the learnings of the demonstrations, we will be able to conduct full life cycle analysis on the economic and environmental side. Lignin use in the Canadian pavement is projected to increase in the future for two reasons. First, paving is anticipated to increase at 3% per year. And second, because we expect increasing market penetration as lignin asphalt becomes more accepted and sought after. The chart shows projected demand if the lignin is incorporated 5, 10, and 20% of bitumen replacement in the asphalt. A major impediment to these projections is the limited amount of kraft lignin produced by Canadian pulp and paper mills. Currently, only one mill produces 10,000 tons of commercial kraft lignin per year. We projected that one mill would start producing lignin in 2024, another in 2025, and a third in 2028. We know that there's a potential for 1 million tons per year. And there are also other markets for lignin that would create a larger demand, far more than what we're seeing on this graph. The technical plan started with a feasibility study, which was completed last year. And then we conducted lab tests with École de Technologie Supérieure, ETS, at their pavements and bituminous materials laboratory. That was completed. We're pursuing on other modules in the future, although for this first phase of the project has been completed. We're going to be putting this on the accelerated pavement testing at University Laval this fall. And there are 2 demonstration trials that are ongoing. I'll talk about that in a second. I just want to highlight that the project is supported by our industrial collaborators and by CRIBE, Emissions Reductions Alberta, Natural Resource Canada, and Quebec Ministry of Forest, Wildlife and Park, as well as BC Forest, Land and Natural Resource Ministry. We're very excited to announce that the first part of the Canadian demonstration of lignin-based asphalt was a success. It was conducted at Sturgeon County in Alberta on August 26, with lignin being incorporated in the bitumen. Stay tuned for the results of the second part of the trial that will be conducted next week in Thunder Bay, Ontario, with lignin being added directly in the asphalt mix. This project exemplifies our new business model, as we're able to work with collaborators on the entire value chain, from lignin producer West Fraser, NORAM, who commercializes the LignoForce system, asphalt producers Park Paving and Pioneer Construction, municipalities of Sturgeon County, Thunder Bay, and Edmonton, as well as university, mainly with ETS. We're here to help for you to exploit lignin. Here's what we can do to help. FP Innovations R&D laboratories have state-of-the-art characterization and process capabilities. In addition, we have a kraft lignin demonstration plant that was constructed within Resolute Forest product mill in Thunder Bay, Ontario. The plant is sized to produce up to 50 kilos a day of lignin and operates on a semi-continuous basis. It offers the flexibility to test black liquors from external mills to produce kraft lignin in the base form, as well as lignin in the acid form. The technical feasibility of producing lignin from black liquor using the LignoForce system can be evaluated at FP Innovations Thunder Bay pilot plant. Laboratory tests and demo plant trials generate data relating to black liquor processability through the various unit operations of the LignoForce system, such as lignin recovery yield, chemical consumption per kilo of lignin produced, as well as lignin product characteristics. These data can then be used to provide accurate estimates on the capital and operating costs associated with the LignoForce lignin plant. Furthermore, the lignin produced during these evaluations can be used for product development purposes and or even commercial scale lignin product trials. We have the capability of preparing all sorts of lignin samples in quantities up to 1,000 kilos, for example, dry lignin at 99%, depolymerized or hydrophobic lignin. FP Innovations also has the capacity to treat 100 metric tons of biomass annually to produce sugars and near-native lignin from the TMP bioprocess. It also operates on a semi-continuous basis. We can also test feedstocks other than wood in this facility to evaluate its response to enzymatic hydrolysis. We can produce sugars at pilot scale and convert them to biochemicals for evaluation. We can also produce near-native lignin for product evaluation at different scale. FP Innovations can help companies develop greener solutions by incorporating lignin into their products. Please contact us should you have any question or if you would like to explore lignin-based products. We would be very happy to help you with that. Thank you.
That was a great presentation. Thanks to FP Innovations for providing that to us. I'd like to introduce our next speaker, Dr. Pedram Patel. He's a professor, a Canada Research Chair Tier 2, an Industrial Research Chair of Chemical Engineering, and a Director of the Biorefining Institute at Lakehead University in Thunder Bay, Ontario. His main research areas include biorefining, lignin valorization, waste management, and colloid and interface science. We'll get that presentation queued up.
Hello, everybody. I hope that you are doing great. Again, this is not a face-to-face meeting because of the COVID, and this is very unfortunate. Hope that I could meet you and discuss with you face-to-face next time, soon. So the topic of my presentation is about the recent progress we have had in the production of water-soluble based product following industrially attractive routes. So you can produce a lot of different products following different pathways. My focus is only on industrial attractive process, and I explain what it means. So why lignin, as Mojgan stated and others stated, basically, well, it's a main part of the agro and wood-based materials. It's available everywhere in Canada and elsewhere. It can be extracted from the material from the pulping liquors very easily, relatively easily, following LignoBoost and LignoForce technology. And we have had two of them commercialized, LignoBoost, LignoForce globally, and we will see more of them hopefully in future. So that means that the lignin is available at a large quantity in many, many countries, including Canada. So one thing that I want to stress here is that we have had a lot of progress on non-lignin based material like cellulose, like hemicellulose and others, sugar and other streams. But basically, if something should be produced from wood, we cannot ignore lignin. It's 1/3 of the raw material. We cannot treat it in wastewater. We cannot simply burn it because it's not going to add values to us. So one way or the other, we have to deal with lignin, even if the main process that we develop is not on lignin. So that's one aspect. The other aspect is that lignin has a lot of potential, has a lot of values. And I just cover one, Mojgan covers another, and we have many, many great researchers who are doing a lot of progress on valorizing lignin. The other thing is that knowledge gap exists for the conversion of lignin to chemicals. So the focus, one of the focus is on Flockland production. As you know, Flocklands are used in water and wastewater purification a lot, and a large volume of that are used. Mainly they are, if we are talking about coagulant, mainly they are alum-based. Because of their low efficiency, a high dosage of them are used. and that generates a secondary pollution by generating a lot of sludge. So sludge handling, sludge dewatering, and so on, they are big problem these days. If you use synthetic flocculant, they are mainly acrylamide-based, they are expensive, ineffective, and oil-based. Dispersion is another one that I focused in my research in the past 10 years. We have been using them in paint and stain for a long time to make sure that the pigments are suspended. But if you go these days to Home Depot, Canadian Tire, and elsewhere and buy new paint and stain, you can notice that they don't smell because they are water-based. So for this new generation of paint stain, we need water-based dispersion, and we don't have too many of them. Fraud flotation of mining is another one. Construction, for example, in concrete, in cement admixture, we need a lot of flocculant to improve the workability of the cement and concrete, especially in cold climate region like Canada. Textile industry, again, for suspending the dyes and to have a good dyeing process, we need to have that. Ceramic, again, for clay suspension, we use a lot. And currently, there are synthetic ones used, they are expensive, and they are oil-based. So what I've been doing in the past 10 years, I focus on 3 different approaches to modify lignin. One was oxidation. So basically, if you oxidize lignin, what happens is that you're going to add some carboxylic group and maybe some other groups to lignin, depending on the reaction. And you are going to open up the ring structure, and you're going to cleave some of the the covalent bonds. So we will have a little bit of molecular weight decrease and yield decrease. So oxidation usually is followed by a yield drop. Grafting is exactly opposite. We are not, let's say, degrading lignin. We are adding groups. We are decorating lignin. So we are adding functional group to lignin. So again, you can produce low to medium molecular weight. Medium molecular weight means the molecular weight of around 50,000, 60,000. But the yield is more than 100% because we are adding things to lignin. Polymerization, again, is another one. But instead of just adding small groups, we can add large monomers and do polymerization and have chain grow and produce very large molecular weight material, let's say in the order of million. So I have followed that, but there are many alternatives route available, but I just follow those that are industrially meaningful. So that means that the main focus was on aqueous-based system, water and atmospheric pressure, no pressurized system. The overall outcome, I could produce a lot of different materials. We have tested them as a dispersant for dye, cement, clay, and many other samples, applications. They have been produced under acidic, alkaline, aqueous, non-aqueous, again, depending on the system. They are suitable for pulping and chemical companies. So that means that the technology we develop can be adopted by the pulping industry because they have water. And there are some chemical companies who used to use a little bit of solvents. So we have options for them too. So the technologies we develop can be adopted readily by companies. We have produced low molecular weight, medium molecular weight, high molecular weight with a high charge. Usually, the charge density of these materials traditionally has been an issue, but it's not an issue for us. We can produce really high charged material. This is a big progress. The main focus of us has been on this red bullet I have. Basically, look, we could and we tried to add many different groups to lignin to produce dispersion, to produce flocculant for different systems. But the question will be, what group is the best to generate the most functional material for that specific application? That's the focus. So basically, we wanted to see if you have municipal wastewater, what's the best alternative? And the best alternative is the maximum functionality with minimum cost and easy operation. So these are some results. So basically, as you can see, the polymerization of lignin under alkaline condition is not new. This is our control we did under alkaline condition, and this is what we did under acidic conditions. So we did all of our polymerization under acidic conditions, so that we have 2 patents with F innovation on that. So we share with F innovation, and that's the real novelty. So as you know, craft lignin is not water soluble at low pH. So we had a suspension polymerization system, but we got much better results. So you can see that the blue line here is we have much better reaction. We had much better system, and these are the products. So when we use, for example, acrylic acid to produce anionic polymer, the water solubility of polymer improved to pH around 4, and it dropped because the carboxylic group we have on acrylic acid has a pK of 4. When we did our polymerization with sulfonate containing monomers, we had the water solubility across the board, even at pH 1. When we had cationic one, we had 100% solubility at any pH we wanted. So producing water-soluble lignin-based polymer is not an issue. Producing high molecular weight polymer is not an issue. Producing high-charge polymer is not an issue. So we have tested our material in the wastewater system. So basically here we compared our product with the synthetic one. The synthetic one is the monomer that we produce under the same condition, but without lignin. So you can see that at different pH, of course, we have different efficiency. But when we compare the yellow and orange one, we can see that we got similar or better result for our lignin containing material. Again, this is for anionic one, and this is for cationic one. So in both systems, so here we are comparing red to green, and the unmodified one is blue. You can see that the efficiency, so the lower the number is better. So relative turbidity shows the clarity of the solution for wastewater. So the clearer, the lower the relative turbidity. So we got better results when we had our material. When we use our material as a sludge dewatering chemical, and we compared with CPAM. Why? Because CPAM is used commercially in pulp industry as a sludge dewatering material, and you can see that the sludge content, the solid content improved a lot. So we had a much better results using our own or in-house generated lignin polymer than commercially produced cationic polymer. We are working on that. We are collaborating with other universities to see how this one can be applied, in different pulping companies. And if you're interested, of course, I will be more than happy to discuss this with you. So we applied our polymers in cities, municipal wastewater treatment. Again, we compare our polymer with the material they use on a daily basis. And again, turbidity is an indicator of the cloudiness or the dirtiness of the wastewater. And you can see the lower the number, the better. So you can see that our material, or even COD, the chemical component of, or the chemical oxygen demand of the water, you can see that we got much better results than the one they are using. When we use that one along with alum in dual polymer system, I can't go to the detail of this figure. So, but what you can see is that this is the alum, the purple one. The red one is the polymer they use in the system. These yellow and orange ones are our polymer along with alum. You can see that our polymer along with alum had much lower turbidity at lower alum dosage, and COD was the same. So conclusion we had here was that if we use our polymer along with alum, we could reduce the alum dosage. For example, if you just use alum, you need 150 milligram per liter. If you use with their polymer, you still need a lot of alum. But if you use our polymer, this point is better. So around 50 milligram per liter. So we could reduce the alum dosage by 60%, 70%. So that's huge, because then again, consider the problem of sludge handling and sludge dewatering and landfilling and so on. So the other process that we worked recently with the help of CRIBE and another pulping company was LignoLignin Process. So this is a brand new process that we developed at Lakehead University. So when you use softwood in a craft process to produce pulp, you get tall oil. Following acid dilution system, you can extract the tall oil and sell it as a byproduct. but there's lignin there because the tall oil production is attached to black liquor evaporators. So they get the tall oil from the evaporator. So some lignin along with the black liquor comes to that. And the current process everywhere is that after getting the tall oil out, they send back the remaining salt and lignin and so on to evaporators and then follow the craft process. So we did some tests, and what we wanted to see is if this lignin after this acid dilution is structurally different from the lignin in here in black liquor. So we wanted to see if acid dilution will impact the properties, if it can be easily separated after acid dilution process, and if we have any application for that, and if the application for that is different from craft process. We have great progress. We have seen interesting results. So because it's about patenting and IP and so on, I cannot disclose much, but if you're interested, we can talk later on if you want to get involved in this project. So, but what I can tell you is that lignotol process is going to generate a different lignin and different opportunities for lignin. So just look back to the polymerization. This is more conceptual thing I just want to deliver after doing a lot of research on lignin polymerization and so on. So what we have seen here is that let's assume that this is lignin monomer or lignin unit. These green ones are the lignin, the monomers we attach. When we do the polymerization, what will happen is that they get attached, they get cross-linked, and at the end of the story, this is going to be the polymer that we will have. So these parts are the lignin parts, the green parts are the monomer or the polymer, the synthetic polymer part. And as you can see, we are talking about a three-dimensional large polymer that includes both lignin and the other synthetic part. What we have seen is that the efficiency of this lignin, as I showed you in the previous slide, is much better than the previous or the commercially used polymers. Why? Because we are talking about a 3D material rather than the linear one. So let's go back again to a structure. If we assume that this is the lignin part, the brown part are the lignin part, the blue one are the synthetic one. So because they have different features, when we add them to the wastewater, and now let's assume that this is wastewater, this is our lignin-based polymer, and these are the colloids. What will happen is that some will interact with the synthetic one, which is quite normal. That's what happens when they add the current commercially used polymer. But what we have is this extra feature that comes with lignin. They currently don't have that one. So when they apply the current used polymers, they can't have this functionality. The other functionality is the blanket effect. Again, because of the 3D structure of lignin, it helps, cover in 3D structure many colloidal particles and push them down. And that's why we have much better results when we compare our polymers with other polymers. So just to wrap up, we have tested our polymerization in aqueous space in system. The concentration of water we have is now up to 50%. We don't need a lot of water. We have tried a lot of different lignin materials. They are all working, and we are now working on reducing the monomer use and maximizing the lignin use. Our process is flexible. It can be used by, you can produce lignin polymer A for company one, polymer B for the second company. You can switch to dispersion production using the same facility. So when we produce dispersion and Flockland, the same facility can accommodate both, and you can produce many different products. So it's like switching from softwood to hardwood. When you do pulping, you just need to tune a little bit the reaction so that you can accommodate both of them. What's going on in lignin research? Basically, I think at pilot scale, we are talking about polymers for wastewater, for sludge dewatering, and lignin nanoparticle. I talk about this one a little bit, but lignin-based for fertilizer, paint, cement, packaging, batteries, and so on, they are coming. For fundamentals, we are talking about hydrogels, aerogels, fire foam, and cosmetic applications. They are big topic. You can see a lot of literature on that, but unfortunately, because of the funding, because of the new system we have in Canada, we don't have too much progress on that, and that's concerning. Just a little bit about lignin nanoparticles. We have done this collaboration with KTH and Abo Academy in Finland and Sweden. So to produce lignin nanoparticle, people use solvent-based system, but now we use water-based system. This is our own technology. We published this one very recently. The properties of our lignin nanoparticle is much better than the previously reported ones. They are water soluble, so we can easily commercialize this process. So these are the picture of the lignin I took in my lab. So as you can see, they have different colors. We have heard this: you can make everything but money from lignin. That was true because of lack of knowledge, because of limited analysis. So we didn't have instrument, we didn't have knowledge. So that was true fact 20 years ago. And we didn't have courage. We could make money out of paper production, out of pulp production. This is no longer valid. Now we have instrumentation, we have knowledge, and we can produce a lot of different products. So again, but the problem we have is some challenges which are related to lignin, and that's coming from the 3D structure of lignin, because simply not all of the chemical sites may be available for reactions. So we should not underestimate the complexity of lignin molecule and reactions. So that means that we need to have expertise to conduct this type of research. This is the, I have only 2 more slides. So you can see that the lignin research is going up. So this is the information I got from Engineering Village data. It's going up dramatically, but in Canada, it's kind of stabilized. And I'm afraid to say that it's going to drop very soon based on what I have seen and noticed on funding and so on across the Canada. So what we need is more funding for pilot scale, for basic research, non-IP research activities. We are open to domestic and international collaboration. Biorefining or BRI Research Institute has invested more than $15 million in research on lignin research. We have advanced tool. We are collaborating very closely with FP Innovations in town, and of course they have pilot plans, and we can collaborate. So if you are interested, you can come. We can help you with lignin research, and we are open and flexible to do research. So I would like to thank our sponsors. We have had private sectors, we have had non-for-profit organization, provincial, federal government. I would like to thank them all. And that's my last slide. So thank you very much for listening to the presentation, and I hope that I can answer your question now. Thank you.
I want to thank Dr. Fatai for his presentation. I'd like to introduce our next speaker, Dr. Mojan Nejad. She's an assistant professor with a joint appointment in the Department of Forestry and Department of Chemical Engineering and Material Science at Michigan State University. Dr. Nejad also holds a professor status-only position at the Mechanical and Industrial Engineering Department of the University of Toronto. Her current research projects are focused on developing lignin-based coatings, adhesives, and foams, and most of them are in close collaboration with industrial partners. Presentation will be loaded shortly.
Hi, my name is Mojgan Nejad, and I'm assistant professor at Forestry Department with joint appointment at the Chemical Engineering Department at Michigan State University. I'm going to start by talking about challenges if you're considering using lignin for bioproducts. One of the main things that you all know is lignin variations. Depending on whether we are using lignin from softwood, hardwood, or annual crops, we're going to have significant variation in lignin chemical, physical, thermal properties. And the variation doesn't end there. Also, if you use different process, like pulping process, chemical pulping process, like craft sulfide soda to isolate lignin from the biomass, those isolation process is going to affect the properties of the lignin too. These lignins that they're isolated from different sources, as you can see in these pictures, over 40 different lignins, they come in different color and different particle size, and they have significantly different properties, again, based on the source isolation method that you use, or even parameters that you use to isolate them. Like, for example, If they use Ligninbased process versus Lignoforce process to isolate lignin from black liquors, we're going to have different properties or different pH temperature or time that is used to, again, isolate lignin from the liquor. It's going to affect the properties of the liquor. The other challenge that we have with lignin, as we saw in this the previous picture, some of them, they have dark color, and for some application, it might limit application of the lignin. But majority of the time, we could use lignin in products so that dark color of lignin will not be an issue, and I'm going to give you a couple of examples through my talk. The other challenge is that with some lignin, as most of the time associated with the craft softwood, we have some unpleasant odor of the lignin that many of these industries, they're working on finding a way to minimize these odors. But if we are considering lignin for very specific application like indoor environment that the odor might be an issue, then we should choose lignin that is isolated from organosolv or soluble-free processes that they don't have this unpleasant odor response. In most cases, because we are dealing with the natural polymers with very complex structures, we have problem with the reactivity of lignin toward co-monomers. That's why it's very important when we are choosing lignin to replace petroleum-based chemicals to measure the reactivity of lignin with co-monomers. And in some of the examples that I'm going to discuss today is like, for example, reactivity of lignin with formaldehyde, reactivity of lignin with isocyanate, or with epichlorohydrin. Low reactivity of lignin is a challenge, and we need to choose lignin that have higher reactivity with these co-monomers. Solubility is another challenge. If we cannot dissolve lignin either in organic solvent or reaction media, in some cases could be high alkaline pH in terms of, in case of, for example, phenolic resin formulation, then this low solubility is significant. It's going to impact reactivity and therefore performance of final products. Inconsistency is another challenge. If, for example, a company is producing craft softwood, if they change the different softwood species or using different material, it's going to affect the properties of the lignin. And every single isolation steps, if they change those parameters, it's going to change the properties of the isolated final lignin too. What most of these challenges that we are discussing today, to some extent, can be resolved if you start thinking of lignin not to be a byproduct. Currently, lignin is produced as byproduct of pulp and paper chemistry or byproduct of bioethanol, lignocellulosic bioethanol productions. And because they are mainly focused on producing high quality paper or high yield sugars or high quality nanocrystalline cellulose, their main focus is on the other products rather than lignin. It's time that we need to think about using an integrated process that would look at lignin as a co-products, not byproducts. In this integrated processes, they simultaneously can focus on optimizing or changing process condition that not only they get high quality paper, but sacrifice to some aspect if they need to do in order to get a really high quality lignin that can be used as a drop-in for other products and not produce lignin as a byproduct anymore. Current pulp and paper industry, if you look at them, they start by using biomass and they use the chips to take in pulp and paper mill to make use the cellulose to make pulp and paper. The bark, they burn it to create energy, and then everything lignin and hemicelluloses that are isolated from pulp is going to be used as to generate steam for pulp and paper, making machines as a source of energy. What we can do, or in future should be done, is that if they start by the biomass, they can also use bark instead of burning to generate steam. They can make value-added products from bark. They can use the numbers that they want and get the other chips or other leftover to make pulp and papers. And then instead of burning lignin and hemicellulose to generate energy, you can basically use lignin to make lignin-based bioproducts and hemicelluloses for other products too. This way, again, lignin, hemicellulose, and even bark are considered as products that they could be used for different applications. There are so much opportunities for creating value-added opportunity for lignin valorizations, to creating high-value products from lignin. I'm going to give you a couple of examples of the projects that I'm currently working, but there are many, many more. But because of the limited time, I'm going to only focus on some of the basic main projects that we're working. One of them is using lignin as a phenol replacement to make lignin-based phenolic adhesives that can be used for plywood and OSB, or by OSB, I mean oriented strand board application. Currently, phenol formaldehyde adhesives or resin that is used for plywood and OSB manufacturing is made of phenol and formaldehyde. Both of them are made of petrochemicals, and formaldehyde is toxic. In the projects that we work and fight for patent, we replaced 100% of the petroleum-based phenol with lignin and 100% of the petroleum-based formaldehyde with glyphosate. Glyphosate is a bio-based and dialdehyde produced from biomass or lipid, and then we mix them together. We were able to formulate a bio-based glue that could be used for plywood application. In this case, when we are using lignin and formaldehyde, we can make a really good formulation for both interior and exterior application. But once we replace also 100% of the formaldehyde with glyphosate, the resin that we had only had very good performance for interior application. It wasn't suitable for exterior application, at least so far, but we're going to work on that. Hopefully we can solve that problem. I have funded projects that I formed a consortium of 2 lignin producer, 1 phenolic resin producer, Hexion, which is the major producer of phenolic adhesives, and 1 plywood producer. We got funding from Canadian government, and our goal is to scale up the production of lignin-based phenolic resin to be tested on the manufacturing line of rose for plywood application by 2023. This is the result that we got. We were able, for the first time, to replace 100% of the petroleum-based phenol with craft softwood, a commercially available lignin that you can see that the bar chart, the green one shows the lignin-based adhesives, and the orange bars are showing commercial adhesives. And the lignin, we call it LF formulation, lignin formaldehyde adhesives generated in these projects has very high, very good and high dry and wet adhesion strength, similar to the commercial based adhesives. And in all the tests that we've done basically we have 100% wood failure, showing that the adhesives perform really good. The other projects is we can use lignin to replace polyol in polyurethanes application that could be used for coatings, adhesives, or foams. When we're talking about polyurethanes, there are 2 major components in polyurethanes. It's diisocyanate and polyol. And they react together to form the urethane linkages. If you look at the structure of lignin, as you can see on the side, it basically has many aliphatic hydroxy group and many aromatic hydroxy group. Basically, the lignin is a natural poly. It's a very complex structures but has this hydroxy group as a natural pollute that we could use it for different pollutants application. We are using, for example, lignin to replace, we were able to do that with 100% replacement of petroleum-based polyol to make rigid foam for insulation spray application for housing. We could use partially replace petroleum-based polyol in flexible foam application that could be used for automotive seatings, mattresses, furniture, anything that they use in polyurethane foam. We have a patent that we use lignin again to replace 100% of the petroleum-based polyol to make water-based, lignin-based PUD formulation, like for coatings application. And the lignin-based pollutants application is another project that is funded by CRIBE that we are going to scale up. I'm going to have another slide to explain that. But these pictures, you can see that we have polyurethanes foams from 0 to 100% petroleum-based polyol was replaced with solid lignin without modification. And these are polyisocyanurate foams with higher thermal, higher fire performance and for insulation application. So as we are increasing the amount of lignin, the color of foam becomes dark. But this is specifically the application that I was talking about, that the dark color of lignin would not be an issue. And the image that you can see that on this side we replace, this is a control foam without any lignin, and after that we replace 20% of the petroleum-based polyol in flexible foam formulation with different lignin. Like for example, the lignin that is coming from peanut shell has a gray color, and the ones with bagasse is light brown, but the other ones have darker brown color. Again, this is for seating application. It's going to be fabricated. You don't see the color of lignin, therefore it's not going to be an issue. As a part of the CRIBE projects that I explained, again, we have two lignin producer. In this case, we have one pollutants adhesives for producer Henkel, who's gonna use the MSU patented technology. We're gonna work with Henkel to scale up production of lignin-based pollutants adhesives. This time for application is in mass timber products such as cross-laminated timber that Element 5 is producing. And this is a preliminary result that we have. The green bar shows the lignin-based pollutants adhesives using craft softwood, and the blue is lignin-based pollutants commercially available adhesives that currently used for CFT. This is a comparative analysis that we applied on the veneer samples. The actual CFT test is different for that, but this is for comparing the two adhesives together. As you can see that we see significant completely wood tear after comparing them together, and lignin-based adhesives has similar dry and wet adhesion strengths to the commercial adhesives and performing really good. And this is a formulation that we're going to work with Henkel to scale up this production and using lignin at the commercial scale. The other project is using lignin as a bisphenol A replacement for epoxy resin application. The epoxy resin can be used for composite application, many composite parts in cars and like other application, for coatings or paint, and for adhesives application. Bisphenol A, I'm sure you all have heard about bisphenol A or BPA-free bottles for the keys that they were banned in Canada, US, and many other countries for using for milk waters for the keys that they were using. But we are still using BPA, even though it's very toxic, for making composite products. And this company, Advanced Biochemical Thailand, they are producing bio-based epichlorohydrin. For epoxy, these are the two main compounds, bisphenol A plus epichlorohydrin. In one project, we replace 100% of the bisphenol A, again with unmodified lignin. And using 16 different lignins, we tested the reactivity with this bio-based epichlorohydrin that we got. This bio-based epichlorohydrin is actually produced from glycerol, and lignin, as you know, is produced from biomass. We mix them together to make epoxidized lignin, and in epoxy resin, we need a curing agent to cure it. For that one, we also use a bio-based curing agent. Is cardolite, and there are different cardolite bio-based curing agent. In this case, this one is produced actually from cashew nut shell. The entire raw materials are bio-based, and we're happy that we could use lignin as a bisphenol A replacement to make bio-based epoxy resin. Now we are working to use this bio-based epoxy resin to mix it with bamboo fiber or other natural fibers to make composite products for cars, make this epoxy coatings for can coatings application, and adhesives. Of course, you know that I'm basically sitting in my office writing proposal and manage the projects. These are my students that this is a picture right before COVID. Some of them graduated, and I have a couple of new graduate students that coming. But the credit should go out to the graduate students and undergrads who are doing the work in the lab. I would like to also thank CRIBE for giving me this opportunity to present and funding my projects. Wood-based composite, NIFA, DOE, and all these industry partners that you're seeing here for funding our projects and providing technical advice. Thank you so much. If you have any question, I'll be happy to answer during Q&A, or you can simply email me if you have.
Okay. Good.
Thanks everybody for their presentations. I just want to review a few housekeeping rules for the Q&A session. So to ask a question, I see a number have come in already. Please input them in the comment section of YouTube or LinkedIn. As I mentioned before, we'll do our best to get as many questions answered as possible. I think we'll start one off with one from Chris.
Yeah, well, thanks again to everybody for the presentations. Those are fantastic. A lot of information, a lot of progress. And I do have to say that I think in the past couple of years, we're really seeing R&D going from the R&D into the sort of the pre-commercial stage, which is critical and important, and it's always been our goal as CRIBE. So on that subject matter, I would like to just pose a question to each of the panelists. As we move forward with greater sort of commercial or opportunities for commercial application, what do you see is sort of the major challenge with getting this into the end user's hands? Getting lignin into the end user and getting commercial applications done. So what is the major challenge? And a quick follow-up on that would be what should be done to overcome those challenges? What needs to happen so we can get greater acceptance? So maybe we can start with, we'll start with FP.
I can give it a try. So I think that there's the classic chicken and the egg challenge for a new industry to uptake a bioproduct such as lignin. They want to make sure that there's going to be enough supply from the lignin side. And on the lignin producers, so if we're looking at craft pulp mills, they will want to ensure that there's going to be enough demand before they invest in converting their black liquor into lignin. So it's really, in order to make it happen, is work hand in hand on the entire value chain to connect the reality of those two industries and working and making a demonstration at scale so that everyone understands what are really the costs and the needs from both sides. I think that's the way to go.
How about Pedram? Do you have any thoughts on that?
Sure. Hi, everybody, and thank you for having me. So I agree with Natasha, what she said. So basically, yes, commercialization, everybody should come, all of us should come together. So on top of the problem we have for or challenges we face for pilot scale commercialization, I think um, the investment, not just financial investment, the time investment, the effort should be more focused. We can see a lot of information coming from a lot of institute, from different companies, but I think if we have some kind of consortium to have everybody who is interested in lignin, from the producer, from the institution, from the end user, all come together, they share their challenges, their view. I think that will be we will have a big step for commercialization of lignin-based products. So I think we should all come together, and that will be that will solve a lot of our problem. Of course, we have had some of this progress, but I think we can do better. Thank you.
Thanks, Pedram.
Oh, I have a motion.
Mojan?
Thanks. I actually think what CRIBE projects are doing is one of the best way to create opportunities, funding research that brings all the value chain industry together. Because there's so much research going on lignin valorization, but having all the value chain industry, lignin producer, product producer, aligned with researchers together to work to solve the scale up problem. That's the best way to start valorization of lignin. And I keep reminding other funding agencies in the US that they should do the same.
Thank you.
Thanks, Mojan.
Okay, so I've got a couple of questions that have been posted here. I'm just gonna, so this is a question for Natasha and Eric. As it's very hard to hydrolyze the lignin, how would your approach to hydrolyze, what would be your approach to hydrolyze the lignin?
When you're talking about difficulty of hydrolyzing, are you mentioning the production of hydrolyzed lignin?
That's what I would assume, Eric.
I think this was a question from Mojan, so maybe Mojan, if you want to ask.
Can you clarify the question? When we talk about the hydrolyzed lignin product, we're referring to actually the hydrolysis of the cellulose. So we're refining the in a very smooth manner to conserve the lignin as near native as possible through the hydrolysis of the cellulose versus a standard pulping where we're valuing the cellulose and using energy and so forth. That creates a somewhat unique kind of lignin, which is a more cross-linked lignin and a more compact structure. So when we talk about hydrolysis, the challenges that we have is maintaining a valuable lignin through the use of smooth conditions and cold chemistry and pH control. For instance, in the use of enzymes, we're able to address these hydrolysis, and some of the challenges are mostly around the preparation of the biomass in order to make the substances or the biomass itself accessible to hydrolysis. So accessing those sugars through the dissolution and depolymerization of cellulose is the challenges, for instance, in softwood and hardwood, and we're working actively on that and are actually pushing forward today and having great results on both those aspects.
Okay, great, thanks. Sorry, did somebody else want to?
I just...
Go ahead, Mojga.
Sorry, Pedram. I think, Eric, part of the questions might have been about, like usually you have to do some pre-treatment before enzymatic hydrolysis, like for example, dilute acid or dilute alkaline pre-treatments. Can you elaborate on that?
Absolutely, and that's really the hurdle in preserving an intact lignin. And when we say intact, is as intact as possible. Obviously, different sources will have and different processing will have different impacts. You don't want to degrade the lignin, creating byproducts and condensation. So actually, for as long as you're controlling the conditions, which are the challenges, by the way, because if you use acids and so forth, you're going to, as Pedram actually showed very well, you're going to start to polymerize the lignins as well, and he's done that quite efficiently. So that's the challenge, is how we're able to convert the biomass in a transformable form without affecting the lignin. Industry has been working a long time to do that, to preserve the pulp and making sturdy and long fiber pulps, and some have succeeded more efficiently than others, and there you see the quality of the pulps. But we have the same kind of challenges now to value the lignin itself. So we've favored enzymatic hydrolysis in those kinds of conversions, but the preparation of the biomass for enzymatic hydrolysis, we're favoring mechanical approaches and soft chemistry approaches to avoid transforming that lignin. I don't know if I've better answered to the question about that.
Okay, good.
Yeah, I think so. Sure. I'd say I've got a question for Pedram. Someone's commented here. Would you mind letting me know the weight ratio of lignin and the polymer used, and what do you think are the challenges of commercializing the process?
So the weight ratio of our lignin to monomers, we are up to 50%, 50%, while keeping the reactivity or efficiency or functionality of the lignin polymer high. So if we increase the lignin ratio a little bit more, we may lose a little bit of functionality, but we are working on this process to have more lignin, less monomers. So that's one aspect. It's an ongoing research. The other aspect is that we use kind of paste environment for reaction. We have only 50 water. We are not talking about dilute system. That's very important. So less volume means less equipment size and so on. So what was the second part of the question?
What do you think are the challenges of commercializing this process?
Okay, so the challenge will be, because we are talking about a market, dewatering is still within the pulp and paper and water, but when we talk about polymers, we are talking about an industry that is not pulp and paper. So we need to have the involvement of other industries, the polymer manufacturing, the material manufacturing, the chemical industry, and end user together to tell us exactly what they need to see in their polymers, what they need to see in the reactions, so that we can all go together. So I think that's the challenge. So we have received a lot of information, but I think we can do a lot better if we have other chemical industries who are the manufacturing of this type of polymers, who know exactly how these polymers are going to be used with us. Then we will have a lot more sensible progress. And of course, that will be more obvious when we talk about pilot scale and commercialization, because I think those companies, in addition to the pulping companies, could be the companies who pick up this process to commercialize.
Another question posed here, a couple of variations of this question. This has to do, I think, with consistency or standardization of lignin. So lignin from different sources, different processes, different batches would all have different properties. We would assume, different species and whatnot. So how do you envision ensuring the uniformity and consistency of lignin materials before using them for your various applications? Or is that even, my addition to this, or is it even important, or is it up to will you be producing them to spec, or do you expect to produce a consistent sort of standardized lignin? So anybody want to jump in and talk a little bit about standardization and consistency of lignin in the marketplace?
Sure. I actually could talk about what's available today, which is kraft lignin. There's the main aspects are twofold. First is good control on the process. Having a strong control over process conditions will be the key factors in the materials produced. The second is also appropriate attribution of applications. you need to be able to specify applications in where the variability of these materials are accounted for and do not have an ultimate effect on the outcome of its use. So if you're using it for a very, very specific and tight specification, it might not be an appropriate use of a, for instance, as refined craft lignin product, for instance, whereas in some applications, small variations have absolutely no impact on the quality of the end product. And that's key to valuing the materials, finding the appropriate way to use it in a context that those variations are insignificant to the quality of the product.
So can I can also add.
Okay, go ahead. Go ahead,
Pedram, go ahead. No, no, this is your time now. I talked last time.
Okay, thank you. So I agree with Eric. So basically, I think we first the simple answer to that is that if you are targeting one application, we should try lignins from different sources, from different species, lignin produced, under different conditions to see experimentally if these variations affect the end use properties of our product. So this is one. Then if you go back to Chris' question, is it important to know if the variability affects the properties? Again, this is a bigger question. I again agree with Eric. For some application, it may be very important. For some other application, it may not. So how do we know? We don't know. So simply because we have a gap of knowledge, we don't know exactly what properties of lignin will impact what sort of applications. There are specific research-based publications, data available, but those are specific. We don't have a big picture to tell that generally when we talk about hydrolysis lignin, we should care about this physical aspect, which is, for example, the surface area, rather than the chemical aspect, because that's going to be the killer, for example. Or when we talk about craft lignin, this aspect we should consider. So that goes back to the comments I have made before. So I think we have had a kind of a consortium or NSERC-based network before in 2000 to 2010 that does not exist. In addition to uh, pushing for commercialization for pilot scale, I think we need to have a group consortium that have many researchers, many industries, and others to bring this type of basic but very important questions so that everybody can answer. So that when we talk about commercialization, when we want to go ahead to the next step, we go with confidence. I think confidence is the most important one when you talk about investment, risk of investment, and so on. Thank you.
Okay, thank you.
Mojan, did you have any thoughts on that?
I just want to add a few points. Based on my experience that we have with characterizing different lignin, majority of the changes can be optimized during the last stage of isolating lignin from black liquor and isolating lignin from lignin cake in terms of biorefinery. As long as the source material is consistent, like for example, if pulp and paper producers is using softwood, keeps using softwood, not mixing hardwood with softwood, and then all the process parameters that they use to isolate lignin from the black liquors is similar, we see less variation in lignin properties. And like I tested in different times, and usually we see very consistent properties if that last part parameters is kept the same. And as Eric and Pedram mentioned, for some application will not be issue. Lignin is a natural glue in the wood. If you use lignin to make adhesives for wood, variation is not going to be an issue. And those are the easy application that we should target.
Thanks, Pedram. I've got another question here. It's directed primarily towards FP Innovations. They mentioned the potential to depolymerize the TMP biolignin to monomers. What is the economic feasibility of depolymerization at the industrial scale? Can you touch on that?
You want to try that, Eric, or
Yes,
if you want me
sorry.
to, yeah, go ahead.
I could start and you could maybe complete on the economic side. Obviously, processing at scale is key. So we're developing scale-up processes to come up to high-yield products. And the yields are, in terms of lignin depolymerization, are related as well as to the composition. So softwood and hardwood will have significant differences in terms of easy to purify, the different monomers. But it's not just about creating those monomers, it's about creating valuable monomers that cover for the fact that you're processing or in a secondary fashion these lignin products from either hydrolysis or even salvation, extraction, and so forth. But there's also one of the key building blocks that in this puzzle will be the residual oligomers, which you typically have, and in valuing those oligomers. So it's a really it's a biorefining approach where you're able to value all the different components of each step of the transformation. And by valuing each of those components, you're able to have a very solid business case. But still today, some of the challenges are in making flow through chemistries that are actually amenable to large scale and ideally automated systems. So those are some of the challenges that we're addressing today at FP Innovations. Natasha, you want to add to that?
Maybe what I would add is that to make it economically viable, you need to look for higher value products. So you may have to convert your sugars and your lignin into converted biochemicals to make them higher value. So instead of selling the sugars and the lignin as is, you may prefer to have some converted products on the line.
Okay. Actually, two more questions for FP on the asphalt project. First question has to do with how does kraft lignin compare to lignosulfonate in asphalt, which is quite a common practice, my understanding is. And the second part of it is, two parts of that question, or two questions on it. Well, to capture them both at the same time here, what type of lignin and concentrations are you using that will still maintain the mechanical and rheological properties? So maybe the first question is what type of lignin are you using and what concentrations, if that can be shared, that can maintain the mechanical and rheological properties? Maybe you want to answer that one first.
Yeah, so I can give that a try. So we're using lignin as refined, kraft lignin as refined. It needs to be dried because it's going to be added to hot bitumen. So we're drying the lignin at 99%. And we're looking into adding it in the bitumen or the asphalt, so the wet mix or the dry mix. We were aiming at higher levels of substitution of the bitumen. So we were looking at 20%. In order to keep only the benefits, we're seeing that up to 8%, we're seeing advantages at high temperatures such as rutting and fatigue. Low temperature, we're seeing cracking that increases as soon as we're adding lignin to higher levels. So if we're talking about lignin non-modified, probably it's going to be below 10% under our northern climates. If we're looking at modified lignin, this is part of a second portion of our projects, then we are looking at increasing that proportion at higher levels. We're looking at kraft lignin because it has to be competitive with the price of bitumen, which is pretty low. Keeping it low priced is better if it's not modified. So that's why we're looking at the lignin as is. There was also a question regarding the lignosulfonates that have been used in in asphalt before. So lignosulfonates are water soluble, so they cannot be used as a replacement of bitumen, such as what we're looking at into with the craft lignin. Lignosulfonates have been used as dispersants, so changing the viscosity of the overall product, or trying to delay the application by changing its rigidity. I don't know if there was another underlying question to
Nope,
that.
nope, that was, those are the two on the asphalt there, so that's good. So maybe we're just gonna have to wrap this up here, running out of time. I see a couple of questions around some of the funding opportunities, participation with CRIBE and other opportunities. One question had to deal with how does the forest industry connect with some of the agricultural applications for lignin, such as soil fertilizer, seed coatings, animal feed, and other things. I would encourage folks to engage with, obviously engage and become a user with Next4, our industry collaboration network, and participate in our collaboration network. We do have relationships with a number of agricultural accelerated organizations like BioEnterprise, Ontario Genomics, BIC out of Sarnia, and a few others globally. So certainly there's ways that we can engage with those organizations and make introductions. And there was actually another question about CRIBE funding and participation outside of Canada to help produce and maybe bring these products to market. CRIBE's primary funding role is to support Ontario industry, create economic development in Ontario, and put Ontario wood to work. However, with that said, we clearly recognize that there are global leaders in this field, and we're absolutely, many of the projects we're working on, our technology is coming from out of Ontario or out of, even out of Canada, whether it's in Europe or the United States. To participate with CRIBE on the funding, you have to have an Ontario partner, and you have to be able to do the trials in Ontario and do the commercialization in Ontario, and we need to see the investment in Ontario. So just to close up a little bit on the rule set there. So I think we're just about out of time. So
can I add something, Chris?
Sure, Pedram, yeah.
So basically, this fertilizer based application, what Chris mentioned, we have had at least 2 different projects on the production of lignin-based fertilizer with collaboration with private sectors. You know that the Lakehead University has agricultural center. We can grow plants and so on. So we have tested a small batch. It was successful. We produced larger batch, and we tested our product in a field in Ontario, and the result was successful. So if you are also interested in lignin-based fertilizers, we have some research activities on that area that will cover, of course, agro-based sector too. So just want to add that that's also some activities that we do at Lakehead University. Thank you.
Great, thank you,
Thanks,
Pedram.
Pedram.
Okay, so myself just want to thank everybody for participating on the panel, and obviously all the great questions. And we apologize if we couldn't get to them all. We will go through the list, and we might perhaps post some responses, summary of the responses as required. But again, thank you again, and pass it off to Mike here.
Yeah, thanks, Chris. I also want to extend my sincere thank yous to everyone participating today. And as I mentioned before, there will be a recording of this session on our Next4 portal. There's a number of other resources there that are probably of value to the folks on the line here. You can register as a user, it's free, and then navigate through the portal to the Lignin section. There's also a number of other material and resources regarding forest innovation and biocomposites. So thanks, everybody.
Thank you.